Dear student, I welcome you all for this control system laboratory wherein we will be able to see the performance of second order system which will be represented by a simple RLC connected to a input voltage. And the standard form of closed loop transfer function of a second order system is given as C of S by R of S, which is equal to omega n square whole divided by a square plus 2 delta omega n s plus omega n square. Here omega n is undamped natural frequency expressed in radian per second, and delta will be the damping ratio. And this is the kit wherein we can able to obtain the frequency response of a second order system. And we do use a signal generator to get a more number of trials. So the kit is can be simulated for 2 kilohertz. In addition of this signal generator, we can go up to 3 megahertz. So the provision of including a signal generator is to get a more frequency input signal for how the second order system will be. So moving on, in today's session, so we will see the objective of this experiment, apparatus required, circuit diagram, procedure, and tabular column, and finally we end up with a demo of the experiment. How we can able to simulate using the kit which is available in our laboratory. So moving on, so the objective is the student will learn how does the second order system can be able to simulate by using a simple RLC circuit and write the transfer function and compare with the standard second order system equation to obtain the damping ratio for different signal. Neither it can be a unit step, unit impulse, or it can be a parabolic input also. The one thing is, so the zeta will change for the unit impulse. So it is given as 1 divided by 1 plus kp. For unit impulse, it is 1 divided by ka. For parabolic signal type of input, so it will be 1 by kv. So the only change you can observe is what is the gain equation we need to substitute for the different rails. So it is, you need to apply limits, that is limit s tends to 0 s into g of s for a unit step and unit impulse. When it comes to parabolic, it will be s square. So that is the only modification that you need to observe if you want to do it for the different input signal. So coming to the apparatus required, so we want a frequency response second order kit, DRB and DCB and DLB, CRO, patch card, signal generator and probe, just to observe the frequency characteristics of it. So this is the kit as I indicated in the front slide itself. So we do have a knob, inbuilt knob, but due to the constraint of 2 kilohertz, so we are adding a signal generator to enhance the frequency up to 3 megahertz. So coming to the circuit diagram, so the frequency response of a second order system. So this is our sine wave signal, and you can set it for the frequency in steps from 100 hertz to 2 kilohertz. But if you want to enhance that, you can go it for the signal generator to increase from 2 kilohertz to up to 3 megahertz. Similarly, the amplitude, the voltage will be giving 6 volts peak to peak, and the peak voltage it will record in the kit. And in additional to that, it will display the frequency, what is the frequency you have tuned in for the second order system to behave, and the phase angle. So in order to record the phase angle, so let me make it clear, in order to record the phase angle, so we need to give it to the reference in, what is the signal you are giving to the system, and another phase shift input, it can be neither from a L or C, as both R, L, C are connected in series. So you can connect at any connection, it will record the phase angle. So here the L and C are fixed, so only we are varying the value of R to note down the zeta value for different case studies. So when it comes to undamped system, the zeta will be 0. So for an underdamped system, so the zeta will be less than 1, that is in between from 0 to 1. So the R should be 1K. And for critically damped system, the zeta will be 1, that is R we have taken as 2 kilo ohm. And for a over damped system, the R will be set it for 3 kilo ohm and zeta will be greater than 1. So here you can able to obtain the characteristic equation, compare and find out the roots for different case studies, and while uploading, while calculating and updating in the tabular column, you can also plot the frequency response for the each system, that is neither a underdamped system, critically damped system or over damped system, with gain versus frequency. So in additional to this, you can able to see how the procedure will. So you need to connect as shown the connection diagram, switch on the main supply to the unit, and the input here is the sine wave with 6 volts peak to peak and 3 volts will be peak on positive off cycle, and you can set it for the frequency from 100 Hz to 20 kilohertz in steps and tablet corresponding output voltage. So here the one thing is what you need to note down here is the L is 104 millihenry and C will be 0.1 microfarad. So you can plot the graph of phase angle versus frequency or gain versus frequency for various value of the damping factor in the semi-log sheet, and you can obtain the inference how the system will behave based on the zeta value. So as I indicated, we will simulate for 3 different cases: undamped, underdamped, critically damped and overdamped. So this is the tabular column. So for underdamped, zeta will be 0.5, the R will be 1. So for different frequency, the input voltage will be set constant, that is 3 volts peak voltage, and the radian you can easily calculate from the frequency. V0 is output voltage, the phase angle will display in the kit itself, and gain is V0 by Vin. If you want in dB, so it is 20 log to the base 10 of the gain. So for critically damped, zeta will be 1, the R will be 2K. For over damped, the zeta will be 1.2. So on similar line, you need to take the reading for 3 different cases and simulate and plot the graph. So these are the sample graphs wherein you can observe the gain in dB with frequency per radian per second. You can plot for angular frequency, or you can plot it for the frequency itself in the board plot. So now we will move on to the demo of the experiment. Now I hope you understood that how we can able to perform the frequency response of a second order system in the kit which is available in our laboratory for different zeta values. So with this, so I will be signing off this online. I welcome all my dear students. So for this recorded demonstration of how we can able to perform frequency response of a second order system. So before going with actual demonstration of the experiment, so let me make it clear. So we are using a kit wherein there are 3 major passive elements, so that are very important. So one is R, so which is varying. So you can see we have set it for 1K, so it is displayed in the multimeter. And L, you can see the L, so which is of 103 millihenry, and C is 0.1 microfarad. So before going with the actual connection, so let me make it clear. So the kit what we are using here, so wherein it will generate a sine wave signal of frequency up to 2 kilohertz. So for that, so we had used an external signal generator wherein we can able to use different, I mean to say up to 20k or up to 3 megahertz. So for that, so we had used an external signal generator to give input for this kit. Okay, so here, so the connection, so let me make it clear for you. So the R, L and C are connected in series, and you can observe here. So from the signal generator I had given input to the reference in. From the reference in it has gone for R, and from R terminal another end to L, and similarly L to C, and from C it is again grounded. Okay, so here in order to measure the phase angle, so we have taken an input, one from signal generator which is the input signal, and another from at any instant of point. It can be from L or it can be from C. Even if you take from L, so it will record the phase angle. Okay, so now let me turn on the module, and you can observe here the frequency I have set it for 100 hertz. Okay, in the signal generator, which is the external signal generator I am using because of the kit constraint, which is of 2 kilohertz. Okay, so here this kit will measure the frequency as well as the phase angle, and this is the output voltage. And let me make it clear here, the peak voltage will be recorded, not peak to peak. Okay, so let me set it for the peak to peak voltage. Here it is 6 volts. I would set using the from the signal generator. So the input here is the sine wave, and the signal voltage is 6 volts. And if you measure in the module, so it will give only the one cycle, so that is a positive cycle of 3 volts. Okay, now I will be setting out for the output voltage in order to record, and the input voltage will remain the same. Let me reset to the frequency. So this is the first trial reading wherein you need to tabulate for different case study. So for the first case study, here we have set it R is equal to 1k, L is equal to L and C remains the same, that is 103 microhenry, and C is 0.1 microfarad. Okay, so for 100 hertz you can record the frequency, it is 100 hertz, and the phase angle for the second order system is 4 degree. So now let me increase the frequency. So you can adjust exactly for 200 hertz using coarse and fine, and you can observe the frequencies of 200 hertz. So what is the phase angle? It is 20 degree, and you need to record it is lagging. And what is the output voltage? It is 5.69. So similarly you increase the frequency to 300. Now the frequency is 300 hertz. You can see the phase angle is 128 degree lag, and the output voltage is 8.05. So like this you need to change the frequency for number of cases, and you need to record the phase angle as well as the output voltage. So now let me directly go to 1k. So you can observe so now I would set it for 1k.
So using the signal generator, and you can observe here, so the phase angle is 175 degree lag, and the output voltage is 0.25. So you can observe, initially the output voltage was 3.4, and for 300 it has reached to 8.5. Now slowly if I increase the frequency signal, so now the output voltage has reduced. So this is the indication that the second order system is attaining to stability. So this is for one value what we had simulated, that is R is equal to 1k. And for a second order system, so the transfer function C of s by R of s is given as k divided by s square plus 2 zeta omega n s plus omega n square. And here based on the zeta we define whether it is undamped, critically damped or overdamped. So for critically damped, zeta is equal to 1. So for that we need to set it for R is equal to, using this potentiometer we need to set it R is equal to 2k. So for undamped system, what we are actually performing using our second order system, I would set it R is equal to 1. So that is called underdamped system. And if I want to observe the performance characteristics, so for a overdamped, okay, so at that case I need to set R is equal to 3k. Okay, so I hope you have understood how we can able to perform second order system and plot the characteristics curve using the kit which is available in our laboratory. Thank you.
Session wherein you will get a more information once you visit our laboratory and do for different trials. Thank you.